Hello everyone, welcome to the talk on fair covering and hitting problems. This is a joint work with Aritra, Banik and Sujoy Bhore. In this work, we study a fair version of several classic covering and hitting problems with respect to some notion of fairness. Let me start with the following problem, which we refer to as the fair covering of points by lines, or FCPL in short. In this problem, we are given a set of axis parallel lines and a set of points in the plane. And each point is colored by a color between 1 to omega. And for each color class, we have a requirement Ri for the ith color class. And the goal is to find a minimum sized subset of the axis parallel lines such that these lines cover at least RT points for each color T. In our example, if the coverage requirements are 2 for red, 3 for blue, and 3 for green, then we can just pick 3 lines and satisfy these coverage requirements. One can similarly consider a hitting version of the problem involving axis parallel lines and points, where instead each line has a color between 1 to omega. And again, each color class has a hitting requirements of Ri, and the goal is to find a minimum sized subset of points such that these points hit at least RT lines for each color T. In our example, if the coverage requirements are 2 for red, 1 for blue, and 3 for green, then we can pick 3 points and satisfy the coverage requirements. The two problems I have described are uh, of geometric nature, but one can similarly define fair versions of graph problems. And in particular, we consider fair versions of vertex cover and edge cover, which are called colorful vertex cover and colorful edge cover. And we will see that fair covering of points by lines is a special version of colorful vertex cover, and fair hitting of lines by points is a special case of colorful edge cover. This is true as in the two geometric problems, we have axis parallel lines and each point can be intersected by at most 2 lines. To formally define the colorful vertex cover problem, we have a graph and each edge is colored by a color, and again we have coverage requirements, and then the goal is to find a minimum sized set of vertices which covers at least Ri edges of color I. And in case of colorful edge cover, the vertices are colored by some color uh, uh, between 1 to omega, and the coverage requirements are R1 to R omega for each color. And the goal is to find a minimum sized subset of edges such that uh, for each color I, at least Ri vertices are covered. So these two problems are generalization of vertex cover and edge cover respectively. So they are as hard as those non-fair version of the problems. Indeed, colorful vertex cover is a well-studied problem, and Bhore et al. Obtained an order of log omega approximation for this problem, where omega is the number of colors. Slavic gave a different approximation algorithm where the approximation factor depends on the summation of requirements over all colors. And indeed, colorful vertex cover is hard to approximate within a factor asymptotically better than log omega. So the log omega approximation by Bhore et al. Is indeed tight. Um, to the best of our knowledge, colorful edge cover was not studied before, but a variant of this problem was studied by Cohen et al. In this problem, the requirements are one for each color class, and the solution set of edges must form a matching. So they studied a colorful variant of matching, where for each color class, I have to cover at least one vertex. So as I mentioned before, colorful vertex cover is hard to approximate within a factor better than log omega. And indeed, this hardness is also applicable for the geometric version of the problem, which is fair covering of points by lines. And one can show a straightforward reduction from set cover, where for each set we have a horizontal line, and for each element we have a color. So we have in total n colors, and the coverage requirement for each color is 1. And this reduction shows that the FCPL problem is hard to approximate within a factor better than log omega, as set cover is hard to approximate within a factor better than log n. So we know that it is not possible to obtain a constant approximation for FCPL in polynomial time. So instead, we ask the question whether it is possible to obtain a constant approximation if we are allowed to use running time, which exponentially depends on the number of colors. And we answered this question in affirmative. We showed that it is possible to obtain almost 2 approximation for colorful vertex cover, and so for FCPL in time n to the order of omega. So if we consider omega to be 1, we obtain the vertex cover problem, and we obtain a 2 approximation in polynomial time, which matches the bound for vertex cover. Our algorithms are based on LP rounding, and in particular via construction of sparse LP, which doesn't contain too many constraints. For the colorful edge cover and FHLP, we design polynomial time exact algorithms. And these algorithms are obtained via a chain of reductions to the colorful version of matching, which was studied by Cohen et al. Now we describe the 2 approximation for FCPL. The 2 approximation for colorful vertex cover is a straightforward extension. Remember that we are given a collection of axis parallel lines and a set of points in the plane where each point is colored by some color. And we consider the natural ILP formulation of this problem, where for each line Li, we have a variable Yi. For each point Bj, we have a variable Xj. And the objective function is sum over all Yi values, which is basically the number of lines selected in the solution. And this ILP has two non-trivial constraints. The first one says that for each color class T, at least RT points must be covered. And the second constraint says that if a point Pj is covered in the solution, then there must be a line in the solution which intersects that point. And we can consider the LP relaxation of this ILP, but note that FCPL contains set cover as a special case. And that's why the LP integrality gap of this LP is at least the integrality gap of set cover LP. And that's why we cannot round this LP in a straightforward manner to obtain a constant approximation. Instead, what we will do is we will round this LP to obtain an additive approximation, and then we will convert that additive approximation to a multiplicative 2 approximation using the desired running time. Now, let's consider any LP solution. To round this LP solution, we will exploit the geometry of the input instance. In particular, the property that each point is intersected by at most 2 lines. And our first goal is to obtain a new fractional LP solution where the cost is increased by at most a factor of 2. And in this solution, each point is assigned to either the horizontal line or the vertical line. That means they gets their coverage from exactly 1 line, not from 2 lines. And to find such a solution, what we do is at first we scale up the Y values by a factor of 2, and then simply assign each point to the line, either the horizontal or the vertical, whichever has the larger Y value. And in this way, we make sure that the coverage of each point is preserved in the new solution. And now observe that each point is assigned to exactly 1 line, but the solution we have is still fractional, and we need to round it to an integral solution. And it is still not straightforward to do that, even if each point is lying on exactly 1 line in the new instance. Instead, what we will do is we will use the disjoint structure of the lines. In particular, now as each point is on a single line, we can express the payoff of each line by a linear function on the number of points on that line. In particular, for the ith line Li and the tth color class, let nti be the number of points on Li from tth color class. Then if I pick the line Li, then for each T, I can cover exactly nti points. And using that structure, we will write down or construct a new LP. And this LP is a sparse LP because it contains a few number of constraints. And this LP has again two constraints. The first constraint again says that you have to cover at least RT points from Tth color class. But the left hand side of this constraint is now just a linear function. We can write down the payoff corresponding to the Tth color class as a summation over NTI times Zi, where Zi uh, is the variable corresponding to ith line. And in this LP, we don't have any variable corresponding to the points. The second constraint says that the number of lines that you can take or summation of Zi is at most k, where k is the cost of the previous LP, which is at most 2 factor of the optimal cost, as we have seen before. And one good thing about this sparse LP is that the fractional solution we had before is also a feasible solution for the sparse LP. And that's why we can say that the objective value of this of the optimal LP solution is at least R1. So what we do is we compute an optimal solution by solving this LP. And this optimal solution will have a good property. So we know that the number of constraints is at most 2m plus omega, where the number of variables is m. And then we can argue that the number of fractional variables in the optimal solution we computed is at most omega, or the number of integral variables is at least m minus omega. And this is true because of the property that the number of linearly independent tight constraints in any extreme point solution is equal to the number of variables. And now, as we have only omega fractional variables, we can round all of them to 1 by increasing the cost by at most omega. And that's why we obtain an additive approximation where the cost is at most 2 plus omega. Now, to obtain the multiplicative constant approximation, we need to show that omega is bounded by at most epsilon opt. That means the opt is at least omega over epsilon. And we can assume that because if opt is at most omega over epsilon, then we can enumerate all the solutions of size at most omega over epsilon. And if any of them returns TS, then we are done. Otherwise, we conclude that opt is at least omega over epsilon. And that's why by using the additive approximation, we obtain the 2 plus epsilon multiplicative approximation. And note that the dependency in the running time on omega comes from the second step. When we compute the additive approximation, we just need a true polynomial time. Next, we consider the colorful edge cover problem and present the polynomial time algorithm we obtained for this problem. Remember that in colorful edge cover, each vertex is colored by a color, and for each color class, we are given a coverage requirement. And the goal is to find a minimum sized subset of edges such that for each color I, at least Ri vertices are covered. To obtain the algorithm for colorful edge cover, we reduce this problem to a variant of matching, which is called budgeted matching. Budgeted matching is similar to colorful edge cover, except here we would like to compute a minimum sized matching which covers at least Ri vertices of color I. And we show that if budgeted matching can be solved in polynomial time, we can also solve colorful edge cover in polynomial time, and we give a simple reduction for that. And in this reduction, given the instance for colorful edge cover, what we do is we add a pendant edge at each vertex of the graph and set the requirement of the new vertices to 0. And then it is not hard to see that if there is a solution for colorful edge cover of size k, then there is also a solution for budgeted matching in the new graph of size k, and vice versa. And thus, using this reduction, it is now sufficient to solve the budgeted matching problem. And to solve budgeted matching problem, we convert it to another matching problem, which is called tropical matching. Tropical matching is again similar to budgeted matching, except here the requirement for each color class is exactly 1. And it is known that tropical matching can be solved in order of n into m time. So we give a reduction from budgeted matching to tropical matching. And note that here in budgeted matching, the multiple coverage corresponding to a color class need to be represented by a single coverage of a group of vertices in tropical matching. And this reduction is fairly complicated, and I have to skip it in this talk. But what we essentially show is if tropical matching can be solved in T_m time, then budgeted matching can also be solved in T alpha n beta omega n square plus gamma omega n square time for some constants alpha, beta, and gamma. And as tropical matching can be solved in order of nm time, we obtain the desired order of omega n cube bound. So to summarize, we obtain 2 plus epsilon approximation for colorful vertex and FCPL. And for colorful edge cover and FHLP, we design exact polynomial time algorithms. And many open questions remain. The first question I would like to pose is it possible to obtain the 2 approximation with better dependency on omega in the running time? For example, is it possible to obtain the 2 approximation in FPT time parameterized by omega? Also, another natural question would be to study other fair versions of graph problems. And there have been some interests in studying fair matching problems. And one might want to consider other graph problems and study their fair versions. And here are the references, and thanks for listening.